So while people are still getting here for the late night research paper reading, I'm going to take a moment to put away my laundry from the dryer. So we will do this in a minute. What's up, people? Is this about order independent transparency? No, this is about simulating water surfaces with wavelet motion, which is sort of, it's like the basic idea of what I had wanted to do, but it's like a more smarter version of it, I think. We'll see. We have to read further into the paper. Please no underwear folding on stream like I would fold underwear. Come on, I'm a dude. So what's going on tonight, everybody? This is yet another day where I just don't really know where the day went. I mean, I did that talk with Casey. That was a few hours, but aside from that, gone. Gone. Volume is low again. Dude, it's the same microphone that I've always used, but turned up by 6 decibels. It's impossible. Making a simple shader language that you compile to the different platform languages. Is that crazy? It is not crazy. However, it's terrible that we have to do this. And it would be much better if we at least did something at least as good as what we had in the past. Okay. Okay, people. Okay, people. Today we are here reading a research paper. If you didn't like that, blame all the people who complain about microphone volume all the time. You know what I'm saying? You do know what I'm saying. Although, it looks like Windows did have it turned down for some reason. I think it resets to 64 once in a while. So now we have to go back and remove some of the decibels, because now I'm sure it's quite loud. No, because OBS has also reset. So OBS reset it to 0 decibels. Well, now it's noisy because the dryer is going in the background. I mean, you want to hear the dryer, don't you? There are videos in YouTube about how macros work. You can watch those. I mean, it changes over time, of course, but those are still relevant. So the paper that we're reading is for this one, which we could watch the video of. I don't understand. This is so compressed. Guys, this looks terrible to me. Let's see if it's any better on... Like, what? How are you a graphics researcher and you upload your video to YouTube in 2018 with this compression ratio that, like, the text is, like, super ringy? Like, what is even going on? How am I supposed to see how good your thing is? I guess that was just the thumbnail that was that bad, but still. It's not good. So assuming that this is computationally reasonable, it definitely looks like something we could just pick up and mostly use, and then add a bunch of knobs to tweak style. Because, you know, something like that, I'm still seeing frames out of order again, but like the hand-painted channel flow there is basically exactly what we want, but not hand-painted a lot of the time. How realistic am I going for in the game? Just watch the video I just put up on YouTube on the channel for that kind of question, because we talked about this for hours today. Yeah, this kind of thing, we don't totally care about this, but we do, like when you drop a rock in the water, we do want to be able to generate some small waves, right? Which is like a simpler version of this. Where you don't affect the solid at all. Yeah, those barrels in the water didn't actually look that good, but that's fine, because that's not what we're doing. All right. So that's what we're looking at here. And we're reading the paper, and sections 1 and 2 of the paper are basically intro. And then 3 is like, hey, we're doing wavelets, which is good because I've done wavelets before. It's been a really long time, but I do have a little bit of background. I mean, the last time I programmed anything in wavelets was probably like 1998 or 1999, but I know how they work vaguely still and remember. So that's good. What about this one, question mark? Fast fluid simulator.
Dear fellow scholars, this is 2-minute paper.
That doesn't look like... I mean, what's your paper? See, this is not, the features that they're showing off is this super fancy splash stuff, which we don't want for this game. We don't care about most of what they're showing. We're not interested in that. And we're definitely not interested, yeah, this is like not... Yeah, this is just not, it's not the kind of thing we're doing. So we're reading about A here, cursive A. And I honestly don't even know what the hell the term wave vector means. I think that might just mean velocity of the wave in each direction, but no, actually it can't mean that. I don't know what the hell wave vector means. Find it intuitive and computationally convenient to represent the wave vector in polar coordinates k. Maybe it is the direction of the wave then. Or not just the direction, because direction would be one dimension, but like direction and speed? I don't know. My style with all this kind of thing is just to skim at first. Like, it's funny because, I mean, I don't know, Feynman was better at learning this stuff than me, but his advice was as soon as you hit something you don't understand, you start over from the beginning. And that's totally not what I do, but maybe I should. But what I do is I just kind of skim it, and if I don't understand something, I'm just like, yeah, whatever. And then I go all the way to the end, and then I decide what to try to figure out next. Like, what do I need to know next in order to, like, if I was going to take action on this, like start programming it, what do I need to do? So direction in vector form? No, because this wave vector has legit 2 degrees of freedom. A direction vector only really has 1 degree of freedom. It's just represented in 2 coordinates. Okay. I represent A on a 4-dimensional grid, X by Y by angle by whatever, magnitude along that angle. Is the coordinate like, what's your index among the basis vectors of the Foyer transform or Wavelet transform or whatever? Is that what it is? Then what's the angle for? I don't know. We'll see. We store samples of A on each of the nodes in the 4D grid, indexed by the coordinates ABC. So 4D already sounds scary to me. Like anything that's 4D is like, Simply because, hey, that's potentially a big grid, right? Like 4 dimensions is more than 3 dimensions, which is more than 2 dimensions. So, but maybe it's, it can be relatively low density. I don't know. Okay. Figure 2. Where is figure 2? That's figure 1. Figure 2. Okay. Schematic of our 4D grid. Oh, so the wave number is like the frequency. Okay. So this is kind of like a 2D spherical harmonic or whatever. Like, so you have a direction, and then you have like an energy level, sort of, for lack of a better word. Doesn't the wave move in 3D? No, it doesn't. Okay. Each spatial location is equipped with a polar coordinate grid. Coordinates x, y, theta, k. We use to store the amplitude of a wavelet. Okay. So these can be very heavily quantized, right? So if this grid were accurate, which who knows if it is, like, okay, so theta is just 8 samples in one dimension, which is not totally awesome, but kind of okay. And then you might be able to get away with further compression, like if your amplitudes are 1 byte or something, right? That's just 8 bytes. That's just a 64-bit integer for that whole dimension, right? So this 4D thing may not be as bad as it sounds. And I think that's part of the point that they're getting to. Right, and also this this wave number thing, I don't know how many of these they're going to have, but similarly, if they could get away with like 8, then, I mean, that's still, I don't know, that's still not great. We'll see. We can now approximate A with a linear combination of basis functions in the style of the finite element method. I don't know anything about finite element stuff. I've never done finite element stuff. C of A in time times phi sub A of x. I don't know what all these things are. Phi sub A of x is a basis function in position. Okay, I know what that means, actually, from doing wavelet stuff. What letter is that? A basis function in angle. Is that like a capital? I don't know what that is. Capital some Greek letter. Rho? Maybe. Rho sub c of theta is a basis function in angle. Okay. I'm not so good at visualizing what a basis function in angle would look like, but I kind of, okay. I don't know. Basis in position I get, though. Okay. Psi is a basis function in wave number coordinates. So coefficient weighting various values. Right. So they're doing a wavelet, but like it's a 4D wavelet, which is kind of trippy. Or maybe it's not. Maybe they don't actually manipulate this. This could just be the formalism. Let's see. Piecewise linear basis functions in all dimensions would set C of ABC equals ABC, or A of A equals, okay, right. Simply hat functions, okay, great. Piecewise linear basis functions in all dimensions. Oh, we read that. The only practical restriction is that our reconstructed function should actually interpolate the discrete samples if we want operations like semi-Lagrangian advection to work as expected. In other words, A of, so ABC is, these are the actual grid values? Or what? Yeah, these are like the integer sample indices on the grid. And so this is just saying, look, if you're sampling the continuous version of the function at coordinates that match your sample centers, you should get the same answer, right? I think that's what they're saying there. Which is fine. It totally makes sense. What's the paper name? Someone literally just linked it. The wave number basis psi c sub k, or psi sub c of k, has a special physical interpretation. It symbolizes the spectrum of the waves represented by the amplitude. All right. Psi describes the shape and frequency space of the wave packet at position x traveling in direction theta with representative. Okay, that's fine, right? So it's like the wavelet transform or the Foyer transform of a wave being in a certain position. Except I don't quite get this, because this is only this is the basis for just one of the dimensions, right? This is the set of basis functions for this dimension right here. The shape and frequency space of the wave packet at position x traveling into, so I guess this is like if you fix these dimensions constant, then, right, because this is like a dense four-dimensional space. So for these two dimensions, for any two selected values of these dimensions, the slot in that array slot is well, it represents, so it represents the exact transform of that thing, right? Which hopefully you don't have to compute. But then if you were to take all the coordinates in this dimension and like average them together, you would, all these transforms are very complicated shapes, right? But by averaging them together, you get like a thing that's the actual shape. I kind of get that. Like, I get that. It's just tying that together with this representation is kind of weird to think about. Okay. A piecewise constant psi of k implies that the wave packet has a flat spectrum with all wave numbers similar to kc having the exact same amplitude. Okay, yeah. All right. So piecewise constant, of course, means a graph that's made out of horizontal lines, segments, right? And so piecewise constant, so however many, we still don't know the resolution of k, like how many samples does this go in that dimension typically, right? Of course you can pick any number, but how many are we planning to use? I don't know. But it's saying for a neighborhood, a piecewise linear, where are we? Or sorry, piecewise constant we started with. Piecewise constant psi c sub k implies that the wave packet has a flat spectrum with all wave numbers similar to kc having the exact same amplitude, right? So that's just like everything in the neighborhood of that grid square. Like if you stored a scalar in there and you had no interpolation, so that meant everything in this bucket has the same value, right? And then what that looks like, if you've ever done a Foyer transform, I mean, it gives you back, depending on how wide that interval is, it gives you back a complex curve in the spatial domain, right? Depending, like if you do a Fourier transform of the entire frequency space, or like if the entire frequency space is just a line, I believe you get back something that looks very noisy, right? Isn't that like the definition of white noise? Or does white noise, like the noise colors maybe require equal energy among all the bands, which might actually mean less presence of higher frequencies because they have higher energy due to shorter wavelength. Anyway, we're getting off topic. I showed some levels that had very good water simulation in your opinion. They don't solve the problems. Did you see today's video where I talked about the actual problems that we have and why they're not solved? Like, if you haven't, let me link that because it is up on YouTube right now. I talk about exactly what we're trying to do, what we are currently doing, pasting that link right now, and that will answer questions that you have along those lines. I'm pretty sure white noise has same amplitude at all frequencies. Okay. One of them does. Okay. A piecewise linear psi gives the packet a bit more of a localized wave packet-like shape. So piecewise linear is like, you know, if you have points evenly spaced along a graph, for example, and you're just drawing straight lines between the points, right? Not horizontal lines, that's piecewise constant. Piecewise linear is you're drawing a line from point to point, right? So piecewise linear gives the packet a bit more of a localized wave packet-like shape. It's just because, you know, it's just a closer approximation to whatever the real value of the function is, you know, in this space, that's all. Because piecewise constant isn't a good representation of anything. And a Gaussian resembles a typical wave packet derivation, yeah. We found it appropriate to use an actual ocean wave spectrum, makes sense to me. So this is probably based on measured data is what they mean here. Equation 32 of Horvath, 2015. We could look that up, but I imagine an earlier paper that Casey pointed me at as well talked about using measured data. Normalized such that, yeah, okay, such that these match. In practice, we found that we can use surprisingly coarse grids. Simulations use big theta, 16 samples for the wave vector angle. Okay, that's more than 8, but still not bad. Finer discretizations did not increase the simulation quality. Wow, okay. So for a game, we probably could cut down on that. We use even fewer samples for discretizing the wave number. We typically need 1. Okay, well, if you need 1, then it's 3-dimensional instead of 4-dimensional. That surprises me. Lastly, the simulations in this paper use real valued A as initial conditions. This function then stays real for all time according to equation 10, so it does not bother to store complex coefficients. Okay. Yeah, okay, so if we look back at what this equation is originally, it's like e to the whatever, right? So, you know, it's e to the I, whatever. That's a complex oscillator, right? So you can imagine having convex coefficient, or sorry, complex coefficients, right? But you know, there are a number of different important equations where, you know, if you don't have any complex coefficients at time t, you won't have any at t plus 1. And this appears to be one of them, I guess, which is nice. I mean, that's not a deal breaker either. Like, it would just need twice as much memory, but it's totally fine. Okay, where are we? The function then stays real for all time according to equation 10. Okay, so it's x by y by 16 by 1. All right, so for example, for a typical game, let's say we want to have, if we have one sample point per grid square, which I don't think is probably enough, but if we did, we would want like 20 by 20 at least. So that's 400 times 16, 6,400. 6,400 numbers to do a whole map. That's very small for what a GPU can do. I mean, it depends on what the math is, but I am not scared of this at all, right? So if instead you have 4 samples spatially in each direction, which I would believe is maybe better, that's times 16 times 6,400. We'll round it up to 8,000 times 16 is, you know, 128,000, which is totally reasonable, again. But it depends on what the math is. It's one slot for the essentially the energy of the wave, right? But that's per. So what it's saying is for everything in the, for each direction, basically, you could have one energy, right? They didn't say how big of a number they need for the energy, but I imagine it's not that high, right? So you could have, you're essentially saying I'm averaging together 16 energies, one for each direction, which is maybe kind of why it makes sense that you only need one, right? Well, but also, well, I don't know. I mean, maybe that doesn't sound that plausible to me. I am not sure, but that's also, we'll see. Can probably drop that 16 directions down to 8. I mean, we'll see, right? We may, if we try implementing this paper, we'll see. Yeah, I was about to say, wait, the one spatial frequency per direction doesn't make sense, because what if your wave is traveling exactly east? Then all the other coefficients are going to be 0, but that's not actually true, right? So you could have a coefficient going east, right, along the x-axis with some energy that's like maybe the primary energy of the wave. Then you can have one going northeast at a different speed with a different energy, and southeast at a different speed with a different energy, or the same, and those will cancel each other out and add to this one, right? And you can do that like with all of these. And so you can actually get, at minimum, if the vertical components needed to cancel each other exactly, then in this 8 version, you'd get 1, 2, 3, 4, you'd get 5 different frequencies, right? So in 16, you would get 9 different frequencies if they had to counterbalance. which is, you could see how adding 9 different frequencies gives you quite a complex waveform, right? If I'm conceptualizing this correctly. Maybe you should smoke less weed and you would understand. Just a suggestion. Let me check the dryer. Does anyone in chat know the name of the paper? It is called Water Surface Wavelets from 2018. Somebody linked it. Ah, there we go. That is the link. So, but yeah, this is basically my style of reading research papers where it's like, sometimes I'll skim over stuff. So like earlier, like these equations, I was like, I mean, there's some integrals. I mean, they claim this is the wavelet transform, which I guess I remember, but I know what the wavelet transform is, so I'm not thinking that much about the math. Exactly. I'm thinking about my understanding of the wavelet transform. These, I'm like, okay, there's like a del and like some stuff, whatever. I just kind of skimmed past that. It was like, look, if I need to know this, I'll look it up later. But the parts that are closer to my current understanding, I'm grabbing and thinking about, right? So like this, like, what does that mean? What can you do with this representation? It's like, okay, don't skim past that if you're close to understanding it, right? You grab it, look at it and think about it. And then even if you end up not implementing this technique, you at least understood something new. Okay. Once you have discretized all of the wave vectors, equation 10 becomes a small number of independent scalar advection equations in space, one for each sample of k. So, okay, this is not obvious if you're not used to wavelets, right? But the whole point of a wavelet transform, if you know the Foyer transform, which is a more popular thing, wavelet transform is like the Foyer transform, but it doesn't go infinitely in space. It's like localized, right? Imagine kind of like you had your basis sinusoids of a Fourier transform or a cosine transform, but they're like multiplied by something that makes them local in space that goes to 0 on the edges. That's called finite support. You could imagine multiplying them by a Gaussian, but that doesn't actually give you the wavelets that people usually use, because if you actually, I take that back. I don't remember. But regardless, most wavelets that people use, the average value of the wavelet is 0, because you want the analogy where each one of these is like a basis vector of a dimensional space, right? Where the dot product of the wavelet with itself is 1, and the dot product of the wavelet with any other wavelet is 0, right? Which is just like the dot product of any basis vector with another vector is 0. So that's, anyway. Mathematically, that makes the wavelets basis functions, right? And then, so where were we? So here when they say this becomes a small number of independent advection equations, what they're saying is like, look, we had this integral or whatever the hell equation 10 was, but because we're treating it as a bunch of slices, And those slices are orthogonal because the basis vectors are orthogonal with each other, and it's sums of those slices, right? So that it's like a trick that's happening here. It's like if you're okay with this approximation, then these slices you don't affect each other. Yeah, they're basis vectors in function space. Yeah. I mean, if you've never seen any of this, you can start by just looking up the Foyer transform, because that is the simplest one. It's not as useful for as many. I don't know. It's useful for stuff. I don't know. Hard to make a claim about that, but it's a little bit. It definitely is a historical precursor to wavelet stuff, and so starting there is a good thing. We're not actually doing code from this right now. We're just reading it, and then I'm probably going to bed. Okay, where are we? Whenever a semi-Lagrangian ray, I'm not up to speed on Lagrangians either. It's like I've read a few times what they are, and I was like, oh, that makes sense, and then I forget because I've never like done anything with them. So, like if I actually work with something, it sticks with me for a long time. Otherwise, it doesn't really. Whenever a semi-Lagrangian ray leaves the simulation domain. Yeah, I don't know what this means exactly. I mean, I guess the simulation domain is like there's some envelope of parameters that is considered to be valid for the whatever operation we're doing. And then we bound it some way by tweaking this. Okay. Amplitudes with different angle theta or wave number k have either different travel direction or speed. Sure. That's what that means. Although I thought, is the wave number like speed and frequency? Or, I don't know. That's what I'm a little bit confused by. Like, this sure looks like they're just saying frequency of the wave. But then they're saying traveling at a certain speed. Like maybe with water, you just assume that each frequency has a fixed speed. Maybe that's some background information that I'm not privy to. I don't know. That's some physics that I've forgotten maybe. Over time, these amplitudes separate from each other, and a nice initial state can turn into a bunch of separated amplitude blobs, as depicted on the left part of figure 3. Without angular diffusion, the wave fronts eventually separate, adding angular diffusion. So you're basically dithering. You're dithering in your quantized space. Right? Dithering is a graphics term. Okay, so I think this is the old one, and then these are the two diffusion terms, where delta controls diffusion in the direction of travel, and gamma controls diffusion in the travel angle, mimicking how wave packets spread out tangentially as they radiate from a source. Other diffusive terms are possible, but we found the two terms work really well. Okay, great. Okay, so they're just like, hey, we just plug in these numbers and they're pretty good. Great. To calculate the actual water height, we numerically evaluate the integral in equation 12. We evaluate the wave number in polar coordinates. Where'd the re come from? Oh, that's the real part of this stuff. And plug in the discretized form of A to get a lot of spam, a lot of Greek spam. Not really. I mean, it's an integral of a product of some stuff, some different functions. Now we can see more explicitly how the basis function relates to the spectrum. Equation 21 treats the basis function as the amplitude function for each wavelength in the height field evaluation. So, you know, we're integrating over all of these, so we're basically adding together a bunch of basis functions along a continuous spectrum of with the magnitude. You know, this is like the inverse wavelet transform or whatever. To use the above formulas, we first precompute the function at the beginning of each time step by evaluating it at a number of discrete sample points. Precompute the capital psi at the beginning of each time step by evaluating it at a number of discrete sample points, like the grid that we're simulating on, right? Oh, no, just a 1D, because it's just a 1D function. Store it in a 1D tension, which we call a texture, which we call a profile buffer. This precomputation allows us to turn this costly integral evaluation into a simple texture lookup for the rest of the time step. Right. So you just pick a resolution that you're okay with. You like linearly interpolate, and there you go. After the precomputation. And so, right, I guess P and T are fixed for the time step. Like T definitely. What is P? Is that how much P is in the pool because you're simulating the water and the different amounts of P will make it behave differently? I don't remember a P. Where'd the P? I don't see a P. Is there a P? Page 8, someone says. Where are we now? Page 8. Anyway, whatever. We'll just keep reading. We don't know what P is. P, maybe P is the variable. What if P is the variable? P is a sample point? Oh, that's kind of gross. Really? No. If P is a sample point, then you need like a 1D texture. You need a lot of 1D textures. You need a giant 3D texture if P is a sample point. We'll see. Unless you can do it one at a time. Let's see. See what they say. Oh yes, discrete sample points P sub I. I'm not sure what Well, what space are these points in, I guess, is the question. Right? Hopefully they're not 2 dimensions of spatial, right? And I assume they're not. I assume this is just some arbitrary. I think this is just parameterized with we'll see. After the precomputation, we can evaluate the water height at any point in space by approximating the one-dimensional integral in 20 with a summation over several sampled angles. Okay. To create our examples, we sum over 400 wave numbers for the precomputation equation 21. Okay. You only do that once per frame, though. That's not that terrible. And we store the resulting psi in a 1D texture of 4096. Ugh. This is starting to sound like a lot. I mean, maybe not. We'll see. Like, it depends on I mean, do you actually, how do you do this integral, right? That's the question. If that's somehow super cheap, then 400 times 4096 is not really that much. It is non-negligible, but not terrible. If, on the other hand, this is heinous, then it's like, ugh. All right, we'll see, though. Because, you know, papers like this often just jump in with extra optimizations later. P is used in a cosine, so it must be a real number. Yeah, I guess so. I mean, you never know when you're looking into shader papers and stuff, because like in HLSL or whatever, whatever. I assume this is a scalar, yeah. I mean, it's not bolded. They're pretty good about bolding their vectors in this paper, right? So it's a scalar. We sum over 120 angles. 400 wave numbers times 120 angles times 4096 samples. That's a lot. I hope they have a good... Oh wait, at each point in space. That's not necessarily in the same function, no. So this function is not including that 120, it's just 400 times 4096. Is it, you know, that's not that bad. I've definitely seen worse. Okay. Note that the number of directions and wave numbers are largely independent. Okay. They chose these parameters and listed them in table 1. Table 2. Figure 4. I don't like this, like, every type of thing. Oh, there we go. Has its own number. I think it should just be like the numbers go up through the paper. So like figure 1, table 2, graph 3, equation 4. Like, just do that, and then I can localize. I don't know where table 1 is otherwise. You know what I mean? Okay. So this is a little bit arbitrary because this is like, I mean, that's a lot, but it's also like for how big of a space are they trying to simulate, right? This is basically, you know, if you want a bigger map, this needs to go up. And if you want a smaller simulation area, this needs to go down. Fortunately for our game, the area we're trying to simulate is not particularly big. So I imagine that this can be quite small compared to what they're used to running. But who knows? Who knows? Maybe for it to look good, it can't be that small. Number of 1D texture samples in profile buffer, 4K. Okay. O of K plus, so O of 400 plus big theta of nu 120 times, whoa, times this squared? Wait, no. No. I guess, oh my God. This is, what? That means 4096 to the 4th. No, okay, no, they goofed. Okay, they goofed. Thank you. This doesn't have a squared in it. So this should just say 4096. I think. Because this is like the total number of spatial locations, right? So these are contradictory a little bit, unless I'm confused. I feel like that's a typo. How are they only taking 4096 samples? They're not. This is basically saying number of spatial grid squares times 120 times 400. So that's 40,000 operations per I mean, that is kind of a lot still. But maybe we can get away with smaller numbers. Oh, wait, I forgot. No, that was this version, right? That was the non-precomputed version. The precomputed version is just 120 per thing. Oh, that's great. That's amazingly better. Okay. Okay. God, it's cold in here. Dude, I can't control the temperature. It's the year 2020 and I cannot control the temperature in my apartment. Let's run their executable. Now that we've read the basic thing, I bet we can find a link to the exe on the web page, and then we could read the rest. So where's the download? Links, executable. I'm downloading wares off the web. All right. It's got the DirectX icon, dude. Okay. Oh, I tried to alt enter it. Okay, this is high-end software from NVIDIA. Don't. Oh my God, guys. Okay, I wanted to be able to read chat and run this program at the same time. Now my text is tiny. Okay, we're just going to keep it in a tiny window here. All right, so this is, if this is what they're saying is the results of their 4K by 4K samples, that is more than we need. We do have a couple maps. Whoa, we do have a couple maps that might be this big, maybe. But for those maps, we can just turn off simulation on a lot of them at a time. So like, that's okay. This is, yeah. So if you imagine we're playing the Sokoban game, right? If this is the resolution of one of the islands that I'm walking around on, this level of water simulation is fine, right? And so for most levels, we get away with way less than 4K. Like, you might want to simulate a bit outside the visual area just to, you know, just for continuity's sake and whatever. But no, this is totally fine for us. I mean, I'm not sure what this should look like in real life. Like, I think if you look at this up close, it's a bit artificial, right? But from back here, well, now we're getting like sampling aliasing and stuff. But oh wait, am I partially over the thing? I'm only a little bit. Let's put it here. Missing some white foam and stuff. Yeah, you can do that procedurally though. Or like you can do that in post if you want to. That's no problem. Like, game developers know how to throw particles at things and whatever and post filter them. Like, this would be a pretty good start. So let's see. Toggle jet ski. I mean, I just want to, like, how do I dump a giant rock into the water? Like, I don't want like a tiny barrel. Like, I want to dump a giant thing in the water. Wave brush. Let's do, how do I like free cam? F3. Okay. I guess we're not really visualizing the amplitude. How do I change the direction? Okay, how do I spray? How do I spray? Oh, do I do that? I think so. I think that's doing it. They definitely could use more tool feedback, but I could see why they didn't do that because it's not really the emphasis of what they're working on. So I'm making it, you know what? We could simulate. Okay, so like our thesis, whoa, what happened there? Okay, our thesis is, where's that island that we had? This is, okay, so like, here's an artifact. I hope they talk about this in the thing. See how you have like preferential sun reflection directions? They don't draw the sun, so I don't know where it's actually coming from. I believe that's an artifact of their quantization, their angle quantization. Like, directions of waves tend to prefer certain ways, certain travel directions. And so the surfaces that you're getting the specular reflections off of tend to be in certain directions. Oh, you think those are clouds? Maybe. I mean, so for the sun, I see how you would get a forward and like a back, but like a side, like we're getting at least 4. I don't know. Maybe I'm misinterpreting. Maybe the sun is directly over my head, and that's just a weird rendering back hit thing. Anyway, okay, so Sokoban game takes place on this island, and we're pushing blocks around from, I don't know, this, the lighting is not ideal, so whatever, but so we would have a river going this way along there. And then it would turn and go this way. Like, it is very, very controlled. Right? Which is good. Like, if you add like the color hacks like we have and stuff, this is not bad. I do think we want wave size to be bigger than this. Like, relative to the island, I don't think we want our waves to be as little, but that's fine because that actually means our simulation grid can be bigger. maybe. Or like maybe we can just bias toward bigger. Like the other paper talked about this, where you could like decide which frequencies you want for each quantum. This is not a very good simulation of what our Sokoban game would do, but you get what I'm saying. Like, I think you take this, you add the color thing, you make it go faster. Let's see what the mesh is. Oh, they're dynamically tessellating it. I don't know if I like that, but... Oh, they're tessellating just by distance. Okay. We'll just do a fixed grid, like, because we don't really need anything bigger than what you see toward like the 4/5 down the screen here. So if we just keep that resolution constant, because our view is mostly overhead, like that's fine. We don't need to do fancy tessellations. Box blast, what does that do? I'm hitting T. Oh, is that if there's a box? I don't know. They sure could have put some more controls in here. SimGrid. I guess that's... Really, that's 4,000 by 4,000. It's a lot of grid squares. So yeah, I feel like if this is 4,000 by 4,000 for this whole map, I mean, I don't know, this is probably 400 or less that we need. And then we could have it, we could get 200 by 200 going on here, which is still like 10 grids per square. That's more than I was thinking, but I mean, the results are going to be good. So yeah, turn off the brush. I still can't box blast, man. I haven't learned Jedi Force box blast. Yeah, so I guess I mean, that's pretty good, man. Oh, there we go. So we didn't have objects turned on. Okay, that's not a very good control. Okay. Okay, cool. That tells us what we're dealing with. Algorithm summary. Main goal is to update the amplitudes and use them to visualize the water height. Nu. I guess that's a nu, right? What letter is that? That's not a nu. What is that? Is that a lowercase gamma? I don't know what that is. Eta. Eta, right. It's been a long time since physics class, man. Eta. We note that almost all of the physics simulation happens in the computation of the amplitudes, and that A is never directly visualized. Clearly, I should have joined a fraternity in college. I would know my Greek letters. It's weird, though, that they say that A is on coarse grids. Because if A was the 4096 by 4096, that wasn't that coarse. All right. One of your professors taught algorithmic complexity using theta instead of big O. Well, theta is a thing in algorithmic complexity. I forget what it is. Like big O is like the expected case, right? Or something, and big theta is the upper bound. I don't remember. I don't remember, man. Theta is equal, big O is less than or equal. Okay. I had it backwards. Or not backwards, but I had it incorrect. I spaced out during the end of this. I just realized. Let me go back to that. Advection step, wave vector diffusion, finishes with the function precompute profile buffers, which it finishes with that. Oh, because then you run the, wait. Gotcha. This really isn't that bad. Except you do need to do it in the pixel shader, and to do shading, you need the gradient of this, which you could do by pixel differences, like by shader gradients, but for small features like this, you're always going to get a better result if you actually do it analytically, which probably involves more math, but it probably shares some of this, so maybe it's not that much more. We'll see. Do I still have the bags of M&Ms and Reese's Pieces? I ate a lot of them, and I mailed a lot of them to someone. The O is really an Omicron. I thought the O was Optimus Prime. They say the gradient is analytic. Okay. Yeah, that makes sense to me. It's just always going to be better if you do that. Rapid wave playback. We don't care about that. Dissipation. I'm not that worried about dissipation. That's a thing that we could do later. Solid fluid coupling, we don't care. Not at all. The basis function controls the wave spectrum, which is visualized in the final results. Yep. That'd be determined by physics or tuned by hand. Figure 6 shows how changing this function right, so here they're just saying, like, look, there are no waves in this frequency range. So we have like a lot of low frequency waves and some highs, but no middles. Okay. I couldn't get the waves to go that much when I was hitting the keys. Wait, if that was a 4 kilometers by 4 kilometers, it's got to be way more than 4096 sample points. If that grid, if that projected grid was the samples. Maybe they, I don't know. These numbers are scary high. But we don't need to do as much as they are, so that's okay. Interesting. Okay. Well, this certainly looks better. Roughly quadruples the runtime. That doesn't sound worth it. I mean, that's definitely different, but not totally sure how much it's going to matter in practical terms. Okay, so that grid that I turned on was the Eta grid, not the sim grid, right? Let's go back here. Let's make the window bigger. Yeah. Okay. So the wave mesh, right? This is their dynamic tessellation situation. That's all fine. Is this just like not, I don't know what that's supposed to be. SimGrid. They say SimGrid. I mean, this looks like, they said it's a 4-kilometer ocean. Maybe they don't simulate the whole ocean at once. I don't frickin' know. I mean, that looks like it could be the Eta grid if that's different from the sim grid. Like, I don't quite get that. Like, if this is the sim grid, this doesn't seem like that coarse of a grid to me. They're saying, oh, we could totally simulate this on a coarse grid. I mean, I guess if the idea is that you're a human scale dude walking around on this map, that maybe that is kind of coarse. But I wouldn't characterize that as coarse for like this kind of view. Okay. The boats would be a reasonable size if each grid square was 1 meter by 1 meter. That's a good point. Yeah, you know what I think it is like there's this thing that happens in games, happened a lot more in older games, where low detail makes you think everything is small, right? So like, I think these are little shrimpy rock islands because they're just some lumpy mesh, but they're actually huge, right? They're actually like this rock here is like 3 times as tall as a human being, right? That makes sense. Yeah, okay. So my brain was just thinking it was smaller because it's just what happens when you don't see like even this lighthouse, like I wasn't imagining what scale that must be. All right, there's a little door for people to go in. So yeah, there's like 3.5 or 4 grid squares for the height of the door. Well, it's moderately coarse. I mean, I feel like that door isn't really to scale, honestly. If this is a meter, that's a little bit of a big... If this grid square is a meter, that door handle is like where my forehead is if I'm standing here. Anyway. Okay. Doesn't matter. Lastly, both the simulation and the wave height evaluation are embarrassingly parallel operations. We like that. We like that. Okay, well, we get the basic idea. I mean, not totally, because like, I didn't think that hard about all this stuff at the beginning. Like this stuff, so I don't actually understand the math exactly. I mean, I kind of get what we're storing in memory and stuff. I just don't really, like, I do not know what Lagrangian advection is, for example. But maybe the next step will be tomorrow to look at the sample code and stuff. Supplementary material. Oh, wait, there was a code. Wait, what? Why did you leave the page? That's... Okay, that's an implementation detail PDF. We'll control click on that. Control click on this. Simplified CPU implementation on GitHub. Source. Not finished 2 years ago. Okay. Some progress. Like what? Wait, is this in C#? What is this? Oh, is that like a lambda? Oh my God. They like wanted this to be as slow as possible. Holy cow. All right. That's why it's taking them so long, is because they want it to be as slow as possible. Implementation details. All right. We read this. Oh, wait. They said all this stuff. To initialize new waves, we simply render an adequately sized quad on each of the aforementioned simulation textures. Yeah, that's fine. Okay, wait. Simulation textures. So P here is a world space position, but it maps to 1D somehow. By dividing it. Dividing the world space position, like what? How do you divide a vector by something to get a real number in 0 to 1? Unless you're doing geometric algebra. D is the physical profile buffer extent in world space units. Oh, this is just like notation. So they're saying like, how far is this from the origin or something relative to this? It tiles seamlessly over all of space. Okay. Well, that'll be useful for when we do wrapping world stuff, but for non-wrapping levels, we can just make it bigger than we actually display. Profile buffer 40 meters. In the pixel shader, we compute a normal for each rasterized pixel. Oh yeah, they didn't cover that in the paper, except, yeah. A 16 directions. Yeah. Distributed to the two closest sample directions. Well, we will not have any non-axis aligned barriers, so that makes that trivial. I don't think I like the looks of the GitHub repository, though, or at least the check-in messages. I mean, does it actually... like, are people actually able to... I guess people are able to build and run it. I mean, it's DirectX 11 or no? Wait, in the paper they said DirectX 11, but that little GUI in the program was the crappy GL GUI that always gets used. So I don't know, maybe somebody ported that? I don't know. Or maybe that's just NVIDIA's GUI and I'm misremembering it as crappy GL GUI. Some progress, yeah, exactly. Like, what is modules? Find imgui.cmake. Great. Data. Harbor. Image to level set. We don't need any of that. So it's at least good. Like, the scary thing would have been to open this up and to see like just 100,000 files, you know? So I'm glad that I don't see that. And like these, none of these matter. Like this is, again, it's like kind of C++ theater. So there's like twice as many files as you need, at least maybe three times. Like these files are just so tiny. Like, I mean, that's good, but let's face it, this should be like 2 files, honestly. Okay. Maybe 3 files. Like, what? Guys, like, what? Who wrote this? Oh my God, guys. Just write a function called spectrum that returns the value. Oh my God. I mean, they're doing this. You could like curry wind speed. Like, why? I don't know. Academia wrote it. No, most of these people work at NVIDIA. Like, if you look at the credits on the paper. Oh, well, no, wait. This says IST Austria. But a lot of the people actually work at NVIDIA. But yeah, never mind. Okay, that I understand this now. Well, guys, this ain't ever going to be fast. Oh, wait, I wanted to see the actual. How do you just see the file? I don't know. Environment. Like, what? Okay. This dude programs in Haskell normally, which is fine. Yeah, like most of this code doesn't do anything, which again is good because that means there isn't that much code. Like, where's the thing? Where's the thing that actually does the precomputation on that profile buffer? Okay, so this is one of the things mentioned in the pseudocode. This is a thing that you would just do like in Vertex Shader or something. It's so weird that they didn't just give out the frickin' shaders, right? Like, what? If you're going to go through all this effort, give me the real version that runs on the GPU, you know? Like, why are you doing this? It's so weird. Yeah, I'm glad there are no factories. Maybe they want to sell something, could be. Yeah, I don't actually want to go through the pain of downloading something from GitHub. I have never, as far as I remember, ever downloaded a program from GitHub. And so I kind of don't want to start now. Factories are actually a thing? Oh, yeah. Oh, yeah, they are a thing. There's just a download zip button. Yeah, well, let me put it this way. I'm fine downloading the source code. I don't actually want to, like, compile it. Because, like, I would have to get, like, CMake and all these things installed. And it's just like, oh, my God, guys. I might get an STD here. Like, there's real dangers involved in downloading software from the internet. All right, let's download this for easy reference tomorrow, so that I don't have to browse GitHub. Download zip. Oh God. Oh no, it'll do it without me having to sign up. Thank you. All right. So we'll look at that tomorrow. You've never successfully built someone's C++ on Windows? Yeah. That's why I'm just like, either I would do this on the Linux laptop or not at all. I'm kind of thinking not at all. So, I mean, I kind of don't. Of course, the problem is if I just go implementing these functions myself, what actually happens is I implement them, I put them together, and it totally doesn't work, right? So then maybe I just get to have the interesting experience of just trying to understand actually what the math does at a high level through the process of debugging. Like for example, like the profile buffer is it's a pre-calculation of that integral for pointwise interpolation. Like I get that. What does that have to do with like they were talking about tiling that over the spatial extent of the map. So like, what are you pre-computing exactly? You're pre-computing an integral of some stuff. Maybe I have to go look at that part again, obviously, right? Like, I don't understand why that integral corresponds to something that repeats over space, or like just goes once over space, right? Like somehow it's a 1D function, but it covers 2D space. So like maybe it's an integral of essentially ever increasing, like from a central point, ever increasingly sized basis functions or something. How would I find the parts that I'm looking for? There's not very much code there. And it looks like a lot of it is named after this is the implementation detail paper. A lot of it seems to be named after the pseudocode, right? So like, for example, if we can actually get this paper again. So here they have this pseudocode, And I saw the advection step function in there. I didn't see that. I was looking for precompute profile buffers and I couldn't find it. I just found the goofy function that makes a profile buffer, like constructs one, but hopefully we can find that. I mean, this looks pretty easy, right? So this is 16. This is the, yeah, that's fine. Or no, like, is this isn't the actual, I don't quite get this, but okay. K dot X plus rand of B. What the hell does that do? And that doesn't, like, what? So this is just the dot product of x with the direction vector for this. Like, we're iterating over all the angles, right? This is the direction vector, Cartesian unit vector for that angle. This is, we're dot producting x with that. So we're saying how much does x go in the direction of this thing? That's fine. This is all totally super vanilla mostly. I mean, this is a little, the 2 pi over is a little bit weird. Except I kind of get it because they're like basis functions. So, okay, but like rand of b, I don't understand what the hell that means in this. Precompute is in the header? Okay, cool. Yeah, I think, my plan so far is that I'll do this implementation tomorrow when I wake up. Who knows? Like I kind of want to like just implement it on the CPU, or as much of it on the CPU as we can, and just let it be kind of slow. But that'll be the most debuggable thing because I hate trying to debug GPU stuff. So we would like implement the wave heights on the CPU. And actually before doing that, like my thing right now, I have this thing that makes a mesh for the ocean, right? That's the size of the map. And that's literally like 2 triangles. So the first thing we would do is make that, we wouldn't even do any of this. We would just make that generate a grid, a regular grid, where you can set how dense you want it in the editor, right? And then that'll be our basis for the height evaluation, and then we can start doing this stuff. Yeah, B is the one based index into the angles. This goes 1 to 16, right? So we go 2 pi, 2 pi over 2, 2 pi over 3, 2 pi over 4. Which I don't really get that. This doesn't, that doesn't make sense to me. Like I thought from the diagrams that this angle was evenly distributed around the circle, which is not what you would get by doing this, right? Or would you? You would get 2 pi. Oh, no, right. That's what this, sorry. I was mentally putting B on the bottom, but that's not what this is. This is the standard thing where 2 pi divided by this is a single pi slice, right? And then this is how many pi slices. So yeah, we're going clockwise or counterclockwise around the circle. Sorry. Can I show the part on the integral? You can just download this paper. It's watersurfacewavelets.pdf. Rand B is a small random perturbation in the direction. Yeah, we'll see what they do in the C++ code. Actually, we have to look. Like, what's the license on this code? Am I allowed to even look at it? Because, like, I don't actually want to copy the code clearly, but, like, license. MIT. Okay, good. If it was like GNU or something, I would be like, get that away from me. If we do not require particular interference patterns, then we can avoid aliasing by adding a random initial phase shift to each wave. Why is that rand of B, though? Oh, I guess I see. What window were we in? So they don't mean randomly repick this every frame for every sample, right? They mean this is a random coefficient that we picked at startup or something, right? Something like that. Okay. For C goes from 1 to K. What was K again? Was K the number of like wave values, which they said would be 1? I think it is. No, this is the number of this is that thing that was like 100 or whatever, right? Where was it? Uh, 400. Number of it's just okay. Just how many samples do we take to integrate this? So yeah, this is just like we loop a bunch. But I don't understand. So they're saying that the runtime of this, the K is factored out. Okay? And that it's just this thing, the number of theta samples. But here, to compute the water height, you do the number of K samples. Okay. So here, yeah, this is the non-optimized version that does not use the lookup table, is what they're saying. It's like, this is the algorithm. This doesn't have the actual part that you care about, which is replacing this with the lookup. Gotcha. Gotcha. Okay, so I was wrong. I was interpreting this as the number of angles, which is like 16. It's not. This is just an integration parameter of how many times do we step around the circle. right? So like, that's 120, right? So 3 degrees per step. Per pixel. I mean, that's a lot, dude. Like okay. It depends. We still haven't looked up how do we figure out the gradient, right? Maybe the gradient makes this loop fall away somehow, or I don't know how it could, but because you don't have to do this per pixel. You have to do 120 of these per vertex of your grid for sure. And then you have to do the gradient per pixel. And the question is, what does that look like? And the answer is, I don't know. I used to think wavelets were so cool, and then they ended up having so few actual uses. Yeah. Yeah, I mean, I don't think I ever did anything super serious. Like, I did a little wavelet image compressor that wasn't trying to be that good back when I learned them, but like, oh, cool. I could write a bitmap compressor and it's not that hard to understand, right? So that was fun, but it wasn't like, competitive with state-of-the-art things. Why did they not just release the shaders? Probably because it's NVIDIA. I don't know, man. Like, NVIDIA probably wrote the shaders. Like, the professor dude probably came up with the algorithm. And NVIDIA probably wrote the shaders. And NVIDIA is very trade secrety, but they still wanted the PR. Like, I don't know, man. It's weird. The wavelet compression relies on vanishing moments, which this paper doesn't even really exploit. That is true. Like, you start to wonder, what if you did a wavelet compression kind of a thing? Like, how many of these coefficients are zero, right? Or close to zero, which is like with wavelet compression, what you do is you drop out all the coefficients that are zero, right? And the trick of the wavelet transform is it sort of puts those coefficients next to each other, things that are likely to be zero. So then it's not that hard to like represent the non-zero things. K is standard deviation. So you're asking for a given slice, how much deviation exists? What? No, I mean K is the direction vector in that direction. Right? I mean, it's literally that. It's cosine theta, sine theta. That's not standard deviation. It is a little weird to me. Like, I guess X is like world space position. I don't understand that part. I don't understand. Maybe we just have to see how this is called. That is the textbook definition of waveform deviation. Really? What? The dot product of a unit vector. No, that's not, that doesn't mean deviation. There's no way. Unless I misunderstand what x is. But I think x is just a world space position. So this is just like, look, we're dotting the world space position. With this angle. Now what's weird is, I must be misunderstanding that actually, because if you assume your coordinates start at 0, 0, and just go to the right and north, you're only going to cover 90 degrees ever with this dot product. So like that's weird. How do you keep your mind sharp as you age? You feel like Twitch has rotted your brain already? Dude, yeah, you gotta take Twitch in moderation, take Twitter in moderation. Those things do actually rot your brain. Technically, tangent K would be the slope of deviation in that. I still don't understand that, but it's clear that I'm confused about something, and so we'll just see. Isn't that implemented in source visualization, water surface shader, GLSL? I mean, maybe. Like, I'm not sure what exactly comes with what we downloaded. So like, I mean, if it's running on the GPU, at least for, like, they may be running all the vertex stuff on the CPU and then just the fragment shader on the GPU or something, right? Except I don't see visualization, water surface shader. Let's see what's there. Not a lot, which is good. Oh my God, dude. So this is like a 2D array, a 2D 4x4 array. They are literally doing the directions as a 2D 4x4. What? So angle. He uses tau instead of 2 pi. All right, so that's a plus. That is the first plus in the category. So yeah. This is so, like, why would you do this? There's a seed. We're going to see the rand. Yeah, so here's the K vector. Here's the pi slice. Okay, this is weird to do it. I guess you're trying to avoid a divide ever, right? So like this is fine. K dir x is the position dotted with K dir plus tau times sine c dot. That's your random number? That's rand. I guess they do it separately. So this is constant per angle. I really don't know if sine of whatever times tau is faster than just using a GPU lookup table, but maybe it is. I don't know anything about that. You better not compute 2 times pi once per pixel per frame. Optimizers for shader languages don't care about that. Like they won't do that. Okay. W is K dir x divided by profile period. Okay, this is the capital D, I guess, from the paper, right? All right, I'm getting tired, so we're going to look at this tomorrow. Oh, let's look at one last question is how much math is the wave normal? And the answer is it's approximately the same amount as the position. It's like almost the same, right? Angle, K dir, same number of steps. It's like literally the same math, except, okay, we cross product these. I don't like that because this is actually a little bit expensive per pixel. Like, why is he using a two-dimensional array? That's so freaky. Yeah, like, I don't like doing this for loop 120 times per pixel. Like, that really does seem like a lot. Right, so this is the so-called profile texture. All right, well, that answers our question about these things. I am honestly a little scared of this. Although it was rendering fine, but okay, here's the thing. Here's where you start getting bitten in the ass, right? Look, it was rendering totally fine. Yes. For this tiny ass window. I guess it's 720p. That's still, like, if you want to render 1080p, how do I... See, we're only getting 100 FPS at 720p on my real good GPU. So, like, this is going to be butt on the Nintendo Switch unplugged, right? Unless we can get away with many fewer iterations for whatever reason. Now, we may be able to. You know, like in this game, oh, I don't know. I mean, the question is what, see, they're not giving me the controls that I actually want, right? So like, I want the slider right here to drop from 120 down to like 10 per pixel or whatever, right? And I want to see the difference. And I can't do that without, I mean, I guess, well, they're probably not hot loading their shaders, but are they actually loading shaders? Maybe not. I guess it's compiled in. Now that said, this is over a much bigger map than we need, right? So the question is, how much of this is per pixel? Like, where is the time going, right? We could pop open Nsight and ask it tomorrow. You know what I'm saying? Like, because if a lot of this time is just because the ocean is so big, it's like, dude, I don't need the ocean to be that big. Not even close. But if a lot of it is just per pixel cost, well, let's look at this. So I'm looking down, it's 100 FPS, right? Looking up, it's about the same. That actually makes me feel good. That makes me think like, well, it's maybe not. It's maybe not per pixel costs. Is it planned for Nintendo Switch? Well, we want to release on whatever we can release on. They don't let you resize the window. Well, I can resize the window, but it may not resize the back buffer that we're rendering to, right? Oh no, it did. I think. Assuming that that number is the actual back buffer number. Okay, so here we're at 120 FPS. Here we're at 60 FPS. So we're really starting to feel it. Like, this is not going to run acceptably at this resolution on most people's PC GPUs today. So then the question is like, how much is this worth it? Is it worth that much CPU? Can we cut down the per pixel costs by like a factor of 4, and does it still look okay? I mean, that's for the estimation of the per pixel angle. I don't know. You know, I almost feel like you should be able to converge faster, because here's the thing. So you already have this grid, because you get this. Let's say in our case, when we're not dynamically tessellating, you have this per vertex, right? That could be passed. You get that for free when you're shading the triangle. That's like a first approximation to your normal, right? And we're not using that information at all. Maybe there's no way to profitably use that information, but I feel like there kind of ought to be. Anyway, we'll see. We could look at this in Nsight tomorrow, but I feel like kind of what we're saying here, whoops, well, kind of what we're saying here is that we're below the water, and now we can't see anything, so we're going to close that. But you lose the nice high frequency octaves. Yeah, it's just, I kind of feel like I don't need quite as much frequency as they have. You know, like part of what they were going for that in that paper is like, you can get down to 3 centimeters. And I'm like, I don't need that much. But we'll see. Maybe you can fake the high frequency with another shader on top of it. Totally. Yeah, like maybe that's just like a normal map that tiles. That's quite possible. Or just like a noise function. So I'm a little worried about it performance-wise. Like, you know, so as an alternative, if we just take the thing that I was showing today during the talk, right? Instead of running a fluid sim, we can just run the particle sim and just put waves on those particles. Like, I don't know. I don't know. I kind of want to implement this and see what I can get away with. You know what I mean? In terms of cutting down the factors. In the presentation, he shows you what it looks like to downsample. Okay, well, we'll maybe watch that in the morning. With such a grid-based, turn-based system, can you not pre-compute a lot of the work? Well, I mean, it's unclear. Probably not. That said, we might, for example, we have regions that are gameplay regions and regions that are not gameplay flow. And so the non-gameplay flow areas might have restrictions on wave frequency that we could use to go faster or something. I don't know. You have less realistic graphics, high frequency would look bad. Maybe. It's just, how much frequency do we lose? We'll watch that tomorrow. I'm very tired. I'm going to go to bed. Thank you, everybody, for coming by, and I'll see you later.